In question 6a, we need to describe how we could accurately find by experiment the data needed to get the Young modulus of a metal wire. Well, first I'll draw a labelled diagram. Here we have the wire under test, which is supporting some changeable masses and holding one half of a vernier scale. Here we have an identical wire supporting the other half of the vernier scale. Using two identical wires cancels out the effect of any temperature changes during the experiment. This length measured from the point of attachment at the top to the point of attachment of the vernier scale. Then we need to measure the length of the wire between the top suspension point and the attachment point of the vernier scale using a metre rule. This length should be as long as is reasonably possible. We need to measure the diameter of the wire in several places using a micrometer and find the cross-sectional area using area is equal to pi times radius squared, or pi times diameter over 2 squared, taking the mean value of the diameter from our measurements. For several known loads on the wire, we need to measure the extension using the vernier scale. Extension is found from the extended length minus the original length, and we must repeat these readings to find a mean. Using the measurement to calculate the stress as force divided by cross-sectional area, and the strain as change in length divided by original length, we can then plot a graph of stress against strain. The gradient of this graph gives the Young's modulus we're expected to find. In B, we have a graph something like this, and in part 1 we need to draw the best line fit through the points, something like this. In part 2, we need to use the line to find the Young modulus of the metal in an appropriate unit. Well, the Young modulus is given by the gradient, stress divided by strain. And so we can do as large a triangle as possible of the straight portion, and this gives the change in y of 5 times 10 to the 7 pascals, the change in x of 5 times 10 to the minus 3. Strain has no units as it is length divided by length. This gives a Young modulus of 1.0 times 10 to the 10 pascals. In C, we're told after reaching a strain of 7.7 times 10 to the minus 3, around about this point here, the wire is to be unloaded. We need to sketch the line we'd expect to obtain for this. Well, the line will go down straight with the same gradient as this line. Something like this.